Okay, this looks good. The screen sharing is also working. Maybe to start with, last time we were looking at Coulomb's law, and we saw that, sorry, I hear myself redundant, so I have to do something about my setup here. Okay, this might do. Okay, yeah, now I don't hear myself again. So we were looking at Coulomb's law, and we were looking what the law is if we have a couple of charges. If we have two charges, then we know that there's a force being exerted on either of these charges. So warm-up question, we have two charges, one charge Q1, which is very large. We have a small charge Q2, and they exert mutual force on each other. So the force on this very large charge, will it be larger than on the small charge? Will it be smaller, or the question, answer C would be, will it be equal? So if you opt for larger, then please give me a thumbs up, or for smaller, or will be the same. Okay, I don't see what do you favor which answer? Say that is for the last one. Okay, that's correct. So the charge, no matter what the charges are, the forces, of course, the larger the charge you have, the larger the force, but the force on each of these charges, they will be of the same magnitude and they will be in opposing direction. So this is what we have looked also last time. And you see here, we have Coulomb, the picture of Coulomb. We have these two charges, Q1 and Q2. And the forces are here in opposing directions because Q1 and Q2 are of the same type. We see that we have a vector that describes the position of Q1, that's R1. We have a vector that describes the position of Q2, that's R2. Both are taken from the origin. We can compose a distance vector from R2 and R1 that describes the separation of Q1 and Q2. We have a balance of forces. That means the force acting on charge 1 due to charge 2, so that's F1 due to 2, is equal in its magnitude by with the charge that is with the force that is acting on the charge 2 caused by charge 1. Then these two forces are parallel, so they both align with the distance vector. And Coulomb detected, or he observed and figured out that the magnitude of that force is inverse proportional to the square of the distance, or specifically to the distance vector. He also observed that it is proportional to the magnitude of Q1 and Q2. So you have here in that formula for the Coulomb force, Q1 times Q2. And there is a constant in there that is given here with gamma, and that gamma is 1 over 4 pi epsilon 0. So this epsilon 0 is a dielectric constant that is determined to be 8.85 times 10 to the minus 12 ampere second per voltmeter. So we saw in this example that we draw the vectors for the force, for the Coulomb force in opposing direction. That does not need to be the case always, because we said there are two different kind of charges. And those charges we call plus and minus. So what happens is if you have some plus charges, they repel each other. Also, if you have minus charges, they repel each other. So not to confuse, minus and minus is repelling each other, plus and plus is repelling each other. So on the other hand, if you have charges here of opposing sign, like a plus and a minus, they attract each other. So you can do that. Going to write here a bit too much. Maybe I'm running out of space, but let's see. So if we express it mathematically, that means if the sine of Q1 is equal to Q2, that means this what I write here, SGN is supposed to be short for sine. Then we have repulsion, and on the other hand, if the sine of Q1 is not equal the sine of Q2, then we have an attraction. So what we have seen here under 1, 2, and 3, that means here the forces are the balance of forces, that they are also oriented, and the proportional factor and the repulsion and attraction respectively, that can be all summarized in Coulomb's law that we are looking at now. So we have our origin, we have our charge Q1 and Q2, dealing with R1 and R2 vectors. We have the distance vector here, we have our forces, and we have our unity vector here. So, and the Coulomb law is now the force F is the force on the charge 2, F2, due to 1 is equal to the force on the charge 1 due to 2, and that is 1 over 4 pi epsilon naught Q1 times Q2 over R2 minus R1. That's a distance vector, but we square it. So because we said the force is decaying proportional to the inverse of the distance square. So I write that here also. Distance vector is R2 minus R1. But then we also have a direction for the force. So now this part of the formula that we have given accounts for the magnitude. Now we have to also include the direction, and that we have said is parallel to the distance vector. It's aligned with the distance vector. So this is R2 minus R1. And of course, we have to get here correct here also, because with the distance vector, we have not only now included the direction, but also a magnitude. So we normalize it to say again by dividing it here by the magnitude here of the distance vector. And this, basically, this expression here, that here is that E that I have plotted in here. So E is given by R2 minus R1 divided by the magnitude of this distance vector. And if you look at it, yes, the magnitude of this vector E is 1. So we have, out of the distance vector, created a unity vector that gives us exactly the direction of the respective forces. So R2 minus R1 is the distance D between Q1 and Q2. So we can give now Coulomb's law in a base-free representation. And so we make this basically a bit more compact now, the formula that I've just given you. So that's F2, and so we had assumed charges of the same type. So F2, and actually that's false general for whether we have because the sign actually enters in the Q. We have the F2, the course on the charge 2 is in opposed direction. So I forgot that sign earlier. So, and that's here our 1 over 4 e epsilon naught. It's Q1 times Q2 times the distance vector R2 minus R1. And we write this here. So, stay here. R2 minus R1 to the power of 3. So, this is our equation number 1, number 1.1, and that's Coulomb's law. So, we have two scenarios. The one scenario is that Q1 times Q2, if you take the product, that they are larger than 0. And of course, that means both of them are either positive or both are negative. That means we are dealing with like charges. Q1 and Q2 are negative, or Q1 and Q2 are both positive. So the other possibility is, another bit of space here. The other option is that we have unlike charges. It means that the product of Q1 times Q2 is smaller than 0. And yeah, so in the first case where we had the like charges, we had the force on the charge 2. For example, it is now proportional to the distance. So you have here the same written as R2 minus R1. And that means you have your Q1 here, and Q2. Here you have our F1. This is our distance here. So here in the first case, you have the like charges. The F2 one is, they are both, I mean, the F2 one basically they repel. And now if you look at the case where you have the unlike charges, then you have the F force on 2 due to 1 is mostly the same, but now you see that there enters, due to the product of these two charges being negative, you have here a minus, and you get R2 minus 1, the distance vector again, and here to the 3. So you see in terms of the scaling in the magnitude, these two cases are not any different, but you have now forces where they attract each other. Choose my template here. I have to rearrange that later. I'll write it on the side now, and I'll shift it afterwards. I want to give you an example for two charges with a specific coordinates of these charges. Two charges Q1 and Q2, and we assign specific locations to them. Q1 is located on R1, and this R1 is 1 times unit vector EX. That means different notation because we go for a coordinate system with X and Y. You can write that here into this bracket, into this vector 1, 0. And the other charge is located, of course, at R2. And R2 is, however, now 2 times EX plus 2 times EY. Or written in more compact notation, that would be Q2. Let's depict that, how that is in the coordinate system. We have here our coordinate system, X and Y. Never forget to label the axis of the coordinates. So our first charge is at 1, 0, 1, 1, and the other one is at 2, 2. Here. So we have basically our vector here. This is 0, 0. This is our origin. We have our vector r1 here. We have the vector r2 here. And we have the distance vector. This is r2 minus r1. And now the question is, in which direction do the forces go? So we have two charges of the same type, so they repel each other, and they go in opposing directions, and the vectors are aligned with the distance vector. These are force vectors. So now we want to solve for Coulomb's law. Coulomb's law is F is 1 over 4 pi epsilon naught. We have the whole thing times Q1 times Q2. R2 minus R1 is the distance vector, and this whole is divided here in the magnitude of the distance vector in the power of 3 here. So let's detail that out further. Let's look at the distance vector in more detail, as we have now these details. So the distance vector R2 minus R1 is E. So R2, you see up there, is 2 times EX plus 2 times EY, and R1 is 1 times EX minus 1 times EX. And now you make the addition or subtraction component by component. That yields you 2x minus 1 EX is 1 EX, and there is nothing you are adding or subtracting from the EY, so you add up 1x plus 2 EY. Or you can write it in this other notation where you put the vectors in these columns. Then you have the first one is 2, 2, and R1 is 1, 0, and then you are doing it component-wise, and you are at the vector 1, 2. It's also matching our, what we have plotted here. You see the distance here is from Q1 to Q2 is 1 in x direction, 2 in y direction. So what is the magnitude of this vector, of the distance vector, R2 minus R1, that you obtain by taking here each element in this distance vector, taking the square of each element. So 1 squared is 1, and 2 squared is 4. And then you take the square root over the sum of all of those. And then distance, the magnitude is the square root of 5. And so you obtain the Coulomb force F21. The force on charge 2 is negative to the charge of negative to the force on charge 1. And we insert that in that we have written up here. Then that would be 1 over 4 pi epsilon naught Q1 times Q2 over square root 5 to the power of 3. And here goes our distance vector. Okay, so that is an example where you have actually used some specific coordinates. And now if you had also given the value for the charges, you can obtain the exact force. Now we have looked at the case where we have two charges, but of course it would be interesting to do that for arbitrary number of charges, and eventually also we want to get here to charge distributions, but the next step would be to see what happens if we don't have only a couple of charges, but if we have an arbitrary number of charges that we can count, and what are the forces that are acting on each of these charges. Okay. We expand that a bit. Now we have a test charge Q that experiences the following force by n charges. So we have Q sub I, and we have running I from 1 to n, and they are placed at various locations, and each location of each charge is denoted with r sub I, and also the I is, of course, then running from 1 to n. Let's plot that, how that could look like. We start again out with an origin. This is our origin, O. Then we have our first charge, Q1. We have a second charge, Q2 here. And we put here third charge, Q3, and so on till we get here to our charge Qn. And then we also put in our test charge, which over here. This is our charge Q. And we want to obtain now the force or the forces or the total force on the test charge due to this multitude of other charges distributed in space here. So this is our vector R. And of course, we have from the origin vectors pointing to each of these charges that we denote them with R1, R2, and R3, and Rn. So this is R1, R2, and 3, and Rn. And each of them is exerting a force now on our test charge Q. So the next thing that when we have obtained all the locations of the various charges, what matters for the Coulomb force is always the distance vector to the respective charge. So we have to put in these distance vectors. So the distance, so the position vector for the test charge, this is just R. So then we have here R minus R2 is a distance vector between the charge Q and Q2. We have here R minus R1. We have here R minus R3. And we have here R minus Rn. So you see this, you can use for an arbitrary number of charges. So, and the idea is now you calculate the total force acting on this test charge by adding up the contributions of each single charge here and doing that by Coulomb's law. So we are about to calculate the total force, and for that we need the force that is acting on Q due to the charge 1, due to charge 2, and so on till we have added the contributions of all n charges. So we do that by a summing up of all force vectors at the position R. So this is you can apply here a superposition principle, and the forces on the test charge is obtained by adding up the contribution of each individual charge that is placed around it. So our job is now to calculate the total force which is acting on Q at the position where Q is, and that is at R. And that's our job to do. So hence we are calculating the force on Q due to charge 1. We are calculating the force on Q due to charge 2. And we keep doing that for all forces, for all charges. To get the total field, or sorry, the total force, which is exerted on Q by the different charges surrounding it, Q1, Q2, Q3, and so on, to Qn. We do a summation of all forces, all force vectors at position R. So we make use of that equation of Coulomb's law that I also made it here above as equation 1.1. We take that one now. So that would be this equation here, right? So that was the case for the scenario where we have two charges. Now we look always test charge along with one of the surrounding charges. And for each pair this Coulomb law applies, and each pair is exerting force on each other, and the total force that is being exerted on the test charge Q is by taking all the contributions of the surrounding charges. So we repeatedly basically use this equation 1.1 and sum the contributions up. So it's 1 over 4 pi epsilon 0. First contribution is charge 1, which is located at R1 on the test charge Q. In the denominator, we get the R minus R, R minus R1 to the power of 3. So this is our general phase free formulation that we have introduced. So this is contribution of the first charge. So we repeat that for the contribution of the second charge. That would be charge QQ located at RQ, and interacting here is R again. So we have again R, this time minus R2 to the power of 3 here, R minus R2. Now we have the second charge counted. The force due to the interaction with the second charge is accounted for. So now let's do the third charge. Let's see that this will be possible to make that a little bit simpler in the notation. So that's our third charge located at R3 with the test charge Q, R minus R3. So now this keeps going on till we reach the nth charge. And also here we have the same way we apply Coulomb's law. So this is actually quite neat because you can see that you can have an arbitrary number of charges that are contributing to the force at the test charge. And of course, you can use the same also to calculate the forces on each other of these involved charges due to the remaining charges and the test charge, because these interactions are always neutral. Yeah, it becomes a bit tedious if you write that for a number. Well, you can make it a bit simpler, and the way to do that, you see a lot of things are written repeatedly here. We do it like that. Let's write that in a more compact fashion and write that the force on the test charge Q is 1 over 4 pi epsilon naught. And then we make use here of the summation sign here and do that, our summation running from 1 to n. Draw that again. That the Q1, the Qi, Ri times Q of R. And here we have then R minus Ri power 3, and here the distance vector R minus Ri. So you see, these are quite compact formulation. Actually, you can make it, you know, that here is equation 1.2. And there's also an important question like the 1.1 or the Coulomb law. But you see, actually, you can make it slightly more compact still and write here F3, because now the test charge is also the same here in all cases. And you can write that 1 over 4 pi epsilon naught, pull out Q from the summation, and then do the remaining factors. And here the contributions of Q sub I, R sub I. So slightly more compact. What have we achieved now? We have achieved a generalization of Coulomb's law for a total of n charges, and we have done this by applying the superposition principle. So the forces that are acting on the charge, you can add up if they are all contributions here um, from the different charges. You have here a linear relation, and a superposition principle applies. So you can think of more complex scenarios. So I also have to write something here on the side. So we have a generalization. We'll rearrange that then later. And make a bit more space to fit it all in one column. We have a generalization of Coulomb's law for n charges. And we have obtained it by applying the superposition principle. Next week, we will then also have tutorial. So we will have number of problems also to work through. So we can apply the Coulomb law. So now you can think of quite complex scenarios. You have here a number of charges that you can, or you can put in a number of charges here. Let's denote them here. And you can also have a test charge, R, or you can also put it somewhere else. And on all these charges, you can see what is the force that is acting on this test charge at the respective location. As you move it around, you will always get a different configuration. You can add the contribution of the various charges onto the test charge. And that is just random what I'm the force vectors now, but in principle, you get a number of charges in this plot here, and these at every point in this area, you can think of putting a test charge and compute what are the total forces on this test charge. And eventually, you can then basically figure out what the vector field is that is in place of this charge distribution, or in this area of various charges. You can move the test charge around, find out what is the force, and plot in this force vector. And that would give you insight into the vector field, which is representing the electrostatic force on Q. So you have here endpoint charges which are at fixed locations. So endpoint charges at fixed locations R sub I. And these point charges are producing a force field. And at each location now in space, you can put a test charge, and this test charge will experience an electrostatic force. So this test charge, you move around, you see what force it is experiencing. Basically, you can compute it with Coulomb's law, and that will generate you or I mean, it doesn't generate, but the field is generated by these test charges, but as you move the test charge around, it will reveal the force at the respective position, and you can monitor also then, or you can compute the total force field that is generated due to this charge distribution, to this particular one. So you have this force field, and at each location, let me write it down to you. At each location in space, our test charge experiences an electrostatic force. And this force, it varies in magnitude and direction. So it experiences an electrostatic force, which varies in magnitude and direction. And we'll see some examples then later on how such a force field could look like. So we have a force field, and that we can all obtain from our equation that we just noted down, 1.2. Take this arbitrary charge distribution given here by the blue charges move your test charge, the red one, around, and at each position you will obtain some force. So, and take all of them together, then this is your vector force field representing the electrostatic force field. So do you have questions regarding this? How you obtain this force field? How you have an arbitrary number of charges? You know their charge value, you know their position, and then you take this Coulomb's law, you can figure out what the force is on a test charge at any position in space. And by doing so, actually, you reveal basically the force field. So we want to take this a bit further. It becomes very convenient then to introduce the concept of the electric field. We have seen that you have an arbitrary number of charges. Each charge contributes to the forces, and we have also introduced the concept of basically using a test charge. So it means the other charges here are fixed in space. We assume them to be now fixed in space here. And the test charge, however, is very small and we can move around and we see what force is acting on it. So this is always in the static case. So you observe what force it experiences. And you see that the other charges are causing these, if you move for the test charge, these other charges cause some reaction. And if you bring in the test charge, it will experience a force. And we can now make use of the concept of the electric field to kind of get here a bit level of abstraction into that. So from the equation 1, that was Coulomb force, and also 1, 2, that was the one where we have the multitude of charges. We know that the charges, they exhibit a long range impact or effect on each other charge. And this is described now by the Coulomb force. So we have here, you see on the top equation, the Coulomb force between two charges. This is equation 1.1. And you have, by applying the superposition principle, forces when you have a multitude of charges. So the force acting on a charge at a position R if there is a multitude of charges that you obtain by the equation 1.2. And this can now be described, or this force field that we have, so we have a force field and you can make use of basically normalizing it or taking out this contribution of that specific test charge and define the electric field. So, you know, here, if you look at the equation 1.2, you have here, I don't know, I can't see when I'm pointing to it. You have here, this is your test charge, while this here are the fixed charges here. And now, what is action on an arbitrary test charge that you bring into this setup where you have a surrounding of multiple fixed charges? You bring in an arbitrary test charge. What kind of force will it experience? For that, you can define the electric field, and the idea is the following. You basically take your force field Q here, F of Q, and divide it by the test charge itself. Then you have an electric field. And this is just by obtained by using here equation 1.2, we divide it by the charge of the test charge itself. So, and this gives us the definition of the electric field. Vector quantities and the force of the electric field, force of the charge. That gives you now here a general definition. So you see the advantage. This far we have a force field with the Coulomb's law. We have a force field on a particular test charge, but depending on what test charge you bring into this surrounding, the force will vary because the force itself depends on the magnitude and of course also on the type of charge. Is it positive, is it negative? But the force that this test charge is experienced depends on the surrounding charges, of course, but it depends on the charge value of the test charge itself. So if you bring in a different test charge, which is, for example, larger, then it will also experience a larger force because by Coulomb's law, the force is proportional to the charge. Well, if you take two charges, then of either charge, or if you take the multitude of charges, it also depends on, as you see here in this equation 1.2, it depends on the charge value of the test charge itself. So you take that out of this equation by simply dividing it through the test charge, you get the concept of the electric field. So the electric field will give you then an answer to what is the force that you obtain if you bring an arbitrary test charge into the electric field. You just multiply the electric field with the charge, and then you obtain the force. So the electric field is something which is, in that sense, also very interesting because it is, well, it is more than just the concept, but it is something which is quite hard to grasp in the sense it is the only way it manifests itself is that it is causing that force as soon as you bring in a charge into the electric field. So a charge within an electric field will experience a force, and in absence of any charges, there the electric field is not really something that you can experience. So it is only showing or grasp, it is only acting upon charges if they are present. But in the absence, the electric field is not hard to capture. So we have here a general definition of the electric field, which is generated by n fixed point charges. So this is the electric field located at r sub I, where I is the number from 1 to n. Okay, so this is the definition of the electric field. And we have questions. We will switch otherwise to some slides that actually enters further into the concept here that we have started to discuss of the electric field. So this elaborates further on what we have been discussing this in the previous minutes also when we were looking at the law force. So you see here setup where you have a positive charge, which is denoted here as a capital Q. It's positive, so it's plus capital Q. And you have here a set of small test charges, or you have a small test charge rather that you can also here place in various positions. Yeah? So you test charge, you move that around your major charge Q, and you expect that according to Coulomb's law, there is a force acting on this test charge. And because this test charge is of the same flavor or the same type as the major charge that you have put in this Q plus, the force is such that this test charge is being actually repelled from that charge plus Q. And you see again that the distance vector that points to the test charge at its various position, it comes all out of the charge Q plus, the capital Q here, and you see, yeah, okay, I can mark here. You see that basically this here in the center is also your origin, so you have your distance vector that goes for the various positions of this test charge radial out of that positive charge in the center, and the force vector is also aligned with this distance vector and is also pointing out from the center. So you move that charge to various positions. You see that according to Coulomb's law, the force will act onto that charge in different directions. Also, we know that according to Coulomb's law, the closer the test charge is to this charge in the center, the stronger the force will act. So when you are using this, if you want to visualize here this electric, this force vector here, then this force vector always originates at the point where it is actually, I mean, you have a force field here, and this drawing into this vector here is a type of visualization of that force field. So the vector is, the base of the vector actually is located here at that position where it actually really is the vector of, that's where it is actually located, right? So here you have a spatial extension of that vector in the depiction, but actually your vector is located only and at a single point in the vector field. And this point where it is actually located, that's the base of the vector. And then you draw it from there and you give it two things. You give it a magnitude and you give it a direction. So the magnitude of that vector actually is represented by the length of that vector here. So if you have a very long vector, that means at that particular point. So here at this is red and red, but if you look here in this point of this test charge, your test charge is very close to the positive charge that you have located. So according to Coulomb's law, which states that the force by magnitude is proportional, inverse proportional to the distance squared of these two charges, you assume because they are very close to each other, you will also have a very large force contribution. So this force, it is located here in the point of the test charge, and it is very large, so you give it a very long, the vector, if you depict it, it will become a very long arrow. While if you go here and move the test charge, for example, here, quite far out, so it is far away from the positive charge, the magnitude of the force is according to Coulomb's law. Again, it is proportional, inverse proportional to the distance vector squared. So you have a large distance vector here now. You'll have a rather small force. You see that the length of the vector becomes accordingly small. And you see that one thing is that is the magnitude. The other thing is the direction. And this is always in all these instances here aligned to the distance vector. So this is also with visualizing using the Coulomb's law, you see that when you want to depict that force field, the electrostatic force field, you have a value for the force everywhere in space, and you have a value regarding the magnitude and the direction. And if you depict these force field by vectors, the magnitude is expressed in the length of the vector, and the direction, of course, is also the direction of the vector, but the value that it represents is actually here at the center of the respective position of the test charge always, and that's where the vector is located at. So now you see in the previous slide, you have seen what the force is according to the test charge. Now we went to the step that we have introduced this electric field, and the electric field is obtained by dividing the force field through the test charge. So we have in some way also normalized it because, or we have, the test charge was, as the name implies, for testing the force field, but now we have a quantity where we can bring in an arbitrary charge, and we know right away what the force will be by multiplying this arbitrary charge value with the electric field at the position in this electric field anywhere, that will give us the value of the force field also. So you see that we have now here these electric field vectors. They are shown in orange, and these electric field vectors show in which direction a positive test charge is moved. The length represents the magnitude of the force. So you see, again, this is essentially the same configurations as in the previous slide. Now we have divided, we've taken out the test charge and obtained from these force vectors the electric field vectors. And you see, just as for the force vector, the electric field vector is of large magnitude if we are looking at a point which is close to the positive charge here, and it becomes very small when you go far away. So the electric field also is, in this case, why? Because it is caused by this positive charge here, plus capital Q here. This electric field is showing, it is derived from, in this circumstance, from Coulomb's law, and you see that this vector field exhibits similar properties, like that the magnitude and the directions behave here the same. We just have taken out this factor from the test charge, and now we can bring in arbitrary charges, and the field will tell us what action we can expect, what force we act on that charge as we bring it into the electric field. Now here we see the other case, and actually we don't have a, so we have this time not a positive charge but a negative charge brought in, and the small test charge here actually is also positive, that we are moving around the test charge, and we want to see what are the force vectors acting on this small test charge as we have a negative charge put in place. Or we would get equivalent results if we were keeping our charge in the center positive and we were moving the negative test charge around. But you see now, because the charge in the center and the test charge which we are moving around of opposite flavor, of different type, one is plus, one is minus, the test charge is being pulled in um, to the major charge here, to the fixed charge that we have placed here in the center of the picture. So forces are attractive, boost the test charge, but also, of course, the charge in the center experiences that force due to the test charge. And we see now the vectors. You see the base of the vector is again originating always in the location of the test charge. So that is the vector is defined it, and that it extends out of that place is just by means of visualizing this force vector. And as we go here further distance, you see same thing that had happened before. The magnitude of the force vector is shrinking according to 1 over r squared. Then we remove this test charge, divide the force field that we could compute, for example, by moving this test charge around. Now we have obtained, in the first step, we have obtained a force value everywhere, but then we divided it by the amount of the test charge, and what remains is this rather abstract concept of the electric field, because you have an electric field if you have here this, now you have a single negative charge here located, and we have here an electric field, but the electric field only reveals itself once you bring in some charge into it. Otherwise, there is no effect that you can tell that there is an electric field. Only in the presence of charge you will notice that there is a force, and so this justifies here the concept of the electric field. So the electric field vectors again show in which direction now a positive test charge is being moved, and you see they are also again aligned with the direction of the position vector, and the magnitude is then direct also proportional to the 1 over r square. Qualitatively, it behaves very similar as, or it behaves the same as the force field in the presence of the test charge. So we define this electric field, and the electric field is defined by the force on a test charge. So electric field is force field divided by Q. So when we have now endpoint charges, then we go back and use our equation 1.2 from Coulomb's law, where we have the multitude of charges being responsible for the force field, and what remains are this multitude of charges, but we have divided again by the test charge. So if you have an electric field which is generated by a multitude of point charges and total, then this is the formulation that will give you the electric field. And you may, for example, assume that these electric charges are all fixed, or at any given point of time they will be fixed, and then you can compute the electric field and also the force that will act on any charge that enters this electric field. The electric field is like the force field, a vector field, and at each location R in space is given by a magnitude and a direction. And that is the magnitude and direction of the force that would be acting on that given point charge Q. So the electric field, to summarize that, is describing the force on an electric test charge. It is charge to force, which is generated by a fixed electrical charge Q. Then this force, it varies with location. So as you move your test charge around, magnitude and direction of that force are varying. It is effective at any location in space, and it is also a vector field. Remember we had the recap in math where we had also the example where we had we had a scalar field and we had a vector field. One was the temperature distribution around the Earth, that was our scalar field. At every position we had scalar value that was attributed to it, and the other one was the airstream over the Earth, and there you had at every position on this, in that case the Earth, you would have both magnitude and a direction for that airstream assigned. So also here for the electric field, any position in your space, you will have a force that is defined then by a direction and the magnitude, and it will act on the charge that you bring into this electric field, this vector field. So it is a vector field, and it shows at each location in space what the force is and what is the force on the positive test charge. Shows magnitude and direction. And what is the unit of the electric field? Well, you have it defined as force divided by charge. Force, you know, is always given by Newton, and Coulomb is the unit of the charge. So that means we have Newton here, and Coulomb is divided. It's divided by Coulomb, and Coulomb is ampere times second. So we can expand here on each side with by meters. Newton meters is watt times seconds. So it's the watt times seconds divided by ampere seconds times meter. And the watt you can also express in terms of voltage times ampere. So what is your power? And volt times ampere times second. You have here in the numerator and the denominator, you have an ampere second times meter, and then you can divide that ampere seconds. So it is a volt meter. So your electric field is given by volt per meter. So the vector fields are represented by vectors and field lines. And the field lines actually are tangents to the vectors of the vector field. I will show you an example then. The direction of the field lines is the direction of the field quantity at the respective location position in space. And the density, on the other hand, of the field lines, that is what we use to visualize the strength of the field. That is basically magnitude of the field quantity. So you see there are two ways to represent that. You can use this by, if you do a visual representation, by plotting in a vector field the respective vectors at selected points, or we use this concept of field lines, and there the lines basically are the tangents to the vectors, and the magnitude is then given by the density of the lines. I will show you then how that is visualized. The electric field, you have the field lines that are pointing in the direction of the force on a positive test charge. So they start at a positive charge and they end at negative charges. So this is just how the field is defined. So the direction, this is basically a convention. You could also, this is the convention that is used. So we start at the positive charge and they point to the negative charge. And field lines at an electric conductor start on the right angle. This I will also tell you then why that is the case. So let's look at here some special case. You have a single charge. You have here the formulation for the general case of the electric field in the, if you have a multitude of charge, but n, let's set it to equal 1. So you have a single charge that reduces here to our equation for the electric field. We just 1 over 4 pi epsilon naught times q naught times the direction vector times its magnitude cubed. That is 4. For r equals 0, only for r0 equals 0, then only this remains. And then we have a monopole field, and now I have this, I want to have this red line in here, sorry, this is not what should be here. I'll get rid of that. Okay. Never mind, think of this line, this around the negative charge not be there, please. So you have a monopole field, and you have here the positive charge Q naught is larger than 0 in the first case, and we depict here vectors for the electric field. So they are pointing away from the charge, from the positive charge, that's by the definition, and they are going in all directions. So there's only a selected number here drawn around that positive charge. And you see, as you go further away, the vectors become smaller. So that means the magnitude of the electric field is decaying by 1 over r squared. So this is a way to visualize it, the electric field for the scenario where you have Q larger than 0. And then you have this second way of visualization that is with the field lines here. So first, the blue ones are you draw in vectors. And then the second here, you have these field lines. So they follow at each, they basically at every point they follow the tangent of the force field vector, but the tangent, as you can see, they all run straight radially out. So also these field lines run radially out, and the density is given by the spacing, or the magnitude of the vector is in the end captured in the how close these field lines run together. You see the difference is here in the blue case. This vector here is of here there you have a large magnitude, and as you go further out, The reducing magnitude is shown by having this shorter vector. Here in the field line concept for visualization of the vector field, the magnitude is given by the density of the lines. And you can see if you are close to this charge here, the distance from one line to the next line, here from one green to the next green, they're quite close. As you move further out away from the charge and you look, the spacing between the lines becomes wider, and that is the indicator of the reducing magnitude in your concept of field lines. So this is different from what you see with the concept of visualizing it by these vectors, the blue ones. And at every point here, the vector has a tangent, but the tangent is, you see these field lines are not bending here. So they go straight out. That means also these field lines, these also going straight out. In the, so then forget that red line, please. This is the opposite case. You have a negative charge. The field lines point towards a negative charge. Again, you have one case of visualization where you use vectors. These vectors are at selected points plotted, and you see the closer they are, the larger the magnitude, and then by becoming shorter, these arrows, that indicates the smaller magnitude, and the direction is given as they point here on that plot. Same thing here for the field lines. They follow the tangent of the vectors, and they are in, yeah, the same concept with the reducing magnitude. So you have narrow field lines here, the center lines. These narrow field lines means that the field is strong, and you have outside weak field, the distance between the field lines is larger. If you go to the case where you have multiple, there you obtain a dipole field. And what I would like you to do, because actually it's not time to close, but what you please could do, and I have to check whether these slides are already up or not, but you can think about how you would plot in these two examples. You have two charges, plus charge here, plus charge here. How do the field lines run? Or you have here two plates where one has all positive charges and the other all negative charges. How do the field lines run for those? And also what happens if you have one charge plus and one minus? How do the field lines run? Please think about that for the next class. And I see our time is up. I thank you for your attention. These slides I will upload today, so you can get them on X site. And think about these three problems with the charges in the charge plate, with the plates with a multitude of charges, how the field lines, how you would visualize them. And I'll see you on next Monday. Looking forward. And yeah, that completes our lecture today. Thank you.